All right, so we're going to talk about computation graphs a little bit. And the idea behind this is that it's a visual representation of something that a computer is going to do in your favorite sequential programming language. But the basic idea is that sometimes we can represent computation graphs in these deep learning frameworks like TensorFlow and formerly Theano and PyTorch. The basic idea is that all we have to do is describe our computation graph with whatever the API gives to us, and then the framework is going to figure out how to make the appropriate computations to do things like gradient updates for neural nets, to do prediction, to compute losses, and so on. So it's very important to understand this, to understand what's going on in these deep neural net frameworks. So let's start with a simple one. So let's think about linear regression. And so in linear regression, the basic idea is that our predict method, it looks like f sub beta of x is equal to x transpose beta. And I'll add in the intercept for fun here to make it a little... instead of absorbing it into the first component of x like I normally do. And so the basic things to note here are that we have certain variables, which are trainable variables here, beta and beta 0. We have input, so let's call these variables. We have an input, which is this x. Oh, I can't write it there. Oh, there we go. We have an input, it's this x, and in general these things, at the moment these are vectors, but in general they're tensors, right? Vectors are just a tensor of rank 1. And so you can imagine that by doing various tensor operations in sequence, you can come up with a, you can represent quite a few different operations in machine learning. So in the computation graph, it starts with your tensors, which in this case you have your input tensor x. We have our variables, beta and beta 0, our intercept. And then typically we think of these as being attached to an edge or an arrow in the computation graph. And so this x, for example, has an arrow associated with it, and you can think of the variable or the tensor as flowing along this arrow, right? And in this case, this tensor just has shape p, right? That's the shape of the tensor. This tensor has shape p, and this tensor has shape 1. It's just a scalar. And then so you have your x and your beta, and then the nodes in the graph, in the computation graph, so these aren't technically nodes, although we need to, they really annotate the edges in the computation graph. The nodes are operations. And, at least we're doing an op level graph, and that's how we're going to talk throughout this, throughout the rest of the course in terms of computation graphs, because it's a little more literally what we're going to code in TensorFlow. So the x and the beta, they're going to go through a matrix multiplication. So we'll just call it matrix multiplication. And this is a node. This is the first node in our computation graph. And what's going to come out of that is x transpose beta. And this is a tensor of shape 1. So it's just a scalar. Now we're going to take this other trainable variable. This is the beta naught, and this is a scalar, and we're just going to add. So we'll draw that as a plus. And then what comes out of this is our x transpose beta plus beta naught, which is equal to our f sub beta of x. Okay, so that's what's going to come out of this operation, right? right? So you can think of this operation, matrix multiply, matmul, takes in two tensors of, in this case of shape P, as input, as arguments, and then it spits out one tensor of shape 1. Right? The other operation in the predict method, in this predict step, is this plus operation. It takes in two scalars and adds them together in this case. And of course, plus is overloaded to work on any two tensors of the same shape you can add together element-wise. And so this is our first computation graph, and this is for the predict method. So this is our computation graph at the operations level. Graph for predict. Right? So this is the simplest computation graph we're going to be dealing with. Now you can further extend this computation graph to add in something like loss computation, right? So you can also have your y, your response. So this will be your yi response, and this is of shape 1, right? And then we can see this is square loss. So we can compute our square loss, or square error loss. And I'm just sort of making up as I go the names I'm going to call these things. Really, these are going to be operations in code, but I'm just going to make up the name square SQR loss in this case. And then what gets spit out of this is the square error loss, which is just our y minus f sub beta of x, space here, squared. So this is the computation graph for predict and loss computation. So this is a bit of an extension of a computation graph. The main thing is that our beta naught and beta here, these were assumed to be input. They're sort of assumed in this case to be fixed, or something that is given to us. But we can imagine a computation graph that is going to allow us to update beta using gradient descent. So our gradient, of course, for the square error loss is just, we have two different things. So let's actually compute these just for fun. So we have our gradient for with respect to beta. So I'm going to just write it as a partial here of y minus our f beta, which is x transpose beta plus beta naught squared. We have that this is just equal to 2 minus, I'll do minus 2, sorry, instead of doing a parentheses there, minus 2 times our y minus just this component, x transpose beta plus beta naught, oops, it should be this, right? And then times x, right? So this gradient, just as a double check, should be of shape P, right? Should be in the same space as beta, and it is, right? Because x is of shape P and the rest is a scalar. Okay, so this is our gradient, and we would like to make a step in terms of this gradient. So the first thing to do for our purposes is to compute this gradient, and we're going to do it visually with the computation graph. Okay. And so to do this, let's just wrap up this whole computation graph here into a single op, and let's call it F, the F op. So let's just call I'll just call it f. It's pretty straightforward. And then, so the way f is going to work, so we first need to compute this inner part here to be able to compute the gradient from the tensors. So we have x, we have beta, and we have beta naught. These all get fed into, these all get fed into f, and what gets output is our f sub beta of x. It's f sub beta of x, and that's what this is, f sub beta of x. Right? Okay, and then the next component, we have our y, right? We have our y, and now let's just extend this out and calculate everything in sequence. So we need to do y minus f sub beta of x, and really it's negative that, and so we can just do f sub beta of x minus y. So there's going to be a minus operation for these. These are scalars, so it's just minus a scalar, and times 2. So we'll just ignore the 2 for now because it's really a sort of a nuisance. And then you also have to take your x and feed it all the way forward to here, and then you get to do a multiply. Right? So this gives us what comes out of here. What is going to come out of here is the gradient with the 2 omitted. Right? So it's going to be this. What comes out is this f sub beta. Oops. What's going to come out is this f sub beta of x minus y times x. That's what's going to come out of these operations. So, so to be able to do something like this efficiently, the basic idea is that we're just going to tell TensorFlow, or your favorite framework, deep learning framework, how to, or what operations you want it to do, and in what sequence. So you're just going to tell it the compute graph. And then it's going to figure out how to execute that compute graph. Now that we have a gradient, we can imagine updating beta. So remember the update rule for beta is beta gets beta minus some eta, and this is at time step t, so eta sub t, times our gradient, right? Which is partial over partial beta of our loss of y and f sub beta of x. Right? Okay. So let's continue building on this. We now have a way of computing a gradient given our gradient, given the we have an extra 2. So let's just also add in the 2. So let's just say in here you also multiply by 2 in this operation, right? Times 2 in this operation, so that we don't have to worry about that 2. So let's wrap all of these operations up. And we can do this just because these are operations, and we can call this grad. Let's just call this the grad operation. Right? Okay, so now we have that. We have that operation constructed. And so let's just complete this by saying that let's do this update. So we have x, beta, and beta naught. These get these all go into the grad operation. The grad operation. And then once we have that, oops, and also y also has to go into there. I didn't, yeah. And then, so this goes into the grad operation, and then out comes our gradient, right? comes our gradient, and we need to multiply by eta sub t. So at whatever our time step t is, we're going to do this multiply. And then, so this is just the multiply. Scalar element-wise multiplied by eta. And then we're going to get, or this eta could be a tensor, and then you would do element-wise multiplication. And then we need to subtract it from beta. So let's bring beta all the way over here. And this is a subtraction here. And then after that, now that we have our update, we're going to, and this is a little bit strange, but we're going to say, now that we have this computed, we're going to assign this to beta. So this is the first cycle constructed. And you have to be very careful about how what cycles do in computation graphs. When I am saying that this is going to be an assignment, I'm going to always mark that, and that should create a cycle, but it's not going to. But I'm not going to create cycles without saying exactly what I'm doing. And so the way that this works is in the compute graph, you can build it all out as long as it's a directed acyclic graph, which means there's no directed cycles. So everything up till now, there's been no directed cycles. As long as it's a directed acyclic graph, then as soon as you tell the framework what the compute graph should look like, or this thing, then your framework is going to be able to figure out exactly how to make those computations in the back end without you specifying any of the details for that, because it might use a CPU, it might use a GPU, it might order these operations in a very specific way. It gets to compile these operations, so it's going to really optimize your compute graph for you. And so that's the basic idea here. But you can see how it's not, the compute graph is not just the predict method, it's the entire gradient calculation and the gradient update. And then explicitly in TensorFlow, once we have this gradient calculation step, we're going to be able to just force the assignment ourselves. And so we'll actually see this play out. But I think it's a good opportunity to think about an exercise for you. So what I want you to do, so this is exercise, and I'm going to say that this is lecture 10. So this is exercise 10.1. What you should do is you should outline in a similar way that I've done it here, the compute graph outline the compute graph for SGD, stochastic gradient descent, with for, let's say, for the hinge loss with ridge regularization. So this is support vector machines. So this is minimizing the hinge loss, which is our well, let's not. This is stochastic gradient descent, so we're not actually going to minimize it in the batch setting. So I'm not going to write it as the batch setting. But the loss is this y minus x transpose beta plus beta naught. Sorry. It's 1 minus y times this, because it's x transpose beta plus beta naught. That's the distance from the separating hyperplane, remember, in the positive direction. And if y is a 1, then this is positive, And so 1 minus that can get to be negative, and then we incur 0 loss, because then we're on the correct side of the margin, plus lambda times beta 2 norm squared. Let's do that. So let's outline the compute graph for stochastic gradient descent for support vector machine type loss, which is this loss here. So go ahead and do that. It should look very similar. And just think about particularly what these objects are, and the main innovation here is the use of a regularization term. So and be liberal about what operations you have available to you, but you should be able to do these just with the basic operations that we've outlined above.